Good morning, students. The previous class we defined the drift velocity and we derived some relations between drift velocity and current density and between current density and electric field. So let us continue that. So in this next I am defining about this one more quantity is there. I am defining the mobility. So the mobility which is represented generally with the mu. So mobility is nothing but this we define this different charge carriers in the different types of conductors. Like in conductors, if you consider only this electrons are the charge carriers, and if you are taking electrolytes, both positive and negative ions, and in case of semiconductors, electrons and holes are the charge carriers. So when they are those are nothing but we called mobile charges. That means those are charging from those charges are traveling from one point to another point, which are the responsible for the flow of this current. And so now the mobility is nothing but we define that mobility as, so mobility of the charge carriers is defined as drift velocity per unit electric field. So that means Vd for E. The drift velocity per unit field is nothing but we called mobility of those electrons there. Mobility of those charged particles. It may be electron or it may be ion or it may be any hole. So the mobility of those charge carriers is defined as drift velocity per unit field, right? And so now this drift velocity we know already that you can substitute here. So we know, and if you want to write the unit here, you can write this velocity as meter per second, and this drift velocity we can write as volt per meter. And so that this is nothing but I can express this as meter square per volt second. So that is a unit here. This is volt second. So that is the unit of this mobility we can write. And we know the drift velocity expression. So we know that drift velocity, magnitude of this velocity is equal to E by m into tau, right? Therefore, you may substitute here. Therefore, mobility we can write this as mobility of the electrons. So then I can write this as E into tau by m by this E. So that E you can cancel. Therefore, this mobility of this electron we can write this as E into tau by m we can write. So that is a mobility expression for this electron here, right? And in case of semiconductors, for example, if you want to calculate the mobility, then due to both positive charges and negative charges, that means due to electron and hole, we need to find there. The total mobility we need to write there, right? So that we will discuss in semiconductors topic. So that is the expression for this definition of this mobility here. The drift velocity per unit electric field is called mobility, and then it is unit is meter square per volt second. And we can express this. This is a basic formula and that can also be expressed like this, right? And so next I will start this Ohm's law. So next let us see about this Ohm's law here. And all of you know that Ohm's law, I think. That means if you are applying some potential difference across this conductor, and so now this some source is connected across this, let us say here, right? And so now this current flowing through this conductor will depend on this potential difference applied across this. If you are increasing the potential difference, then automatically current should also increase there. And so if such a relation is there, then we can write this as V is directly proportional to this I, right? And so that means we can conclude it as when the physical conditions of the conductor remains constant, the current flowing through it is directly proportional to the potential difference applied across it. So then that is nothing but we state that as this Ohm's law there. When physical conditions remains constant means like temperature and pressure and other conditions like physical conditions remains constant, then the current flowing through the conductor is directly proportional to the potential difference applied across it. So that means I is proportional to V. So that I am writing here as V is proportional to I. So then we can write this expression as we can introduce a constant here. So write the statement there, statement of that Ohm's law. When the physical conditions like temperature and pressure, when physical conditions like temperature and pressure of a conductor remains constant, then current flowing through the conductor is directly proportional to the potential difference applied across it. Right? So that is, we can express it as V is proportional to I, or so let us write in according to the statement only. We are saying this I is proportional to that of V, current is proportional to the potential difference applied here. So I can write this as I is equal to 1 by R into V. Now this 1 by R is nothing but we consider it as a constant, and so that we can write this as V is equal to IR. Where R is constant called a resistance. All of you know that. So that R is called now resistance. Therefore, this resistance R is equal to, I can write this as V by I. So this is a mathematical form of this Ohm's law we can write. So then actually here this is the equation here, the relation between potential difference, current and resistance. And so from that we are defining that resistance as V by I. And so about this resistance we will discuss later, just after completion of this Ohm's law. So then there is a resistance definition. We are introducing a proportionality constant, and that proportionality constant we are naming that as a resistance, right? And so now here this Ohm's law is not the basic law, or it is not the universal law, right? It is just a formula, and this Ohm's law V is equal to IR is a formula, and Ohm's law means actually this proportionality should be valid there, right? And so now there are certain conductors there are certain materials which obeys this Ohm's law. Those materials are nothing but we called ohmic conductors, and for ohmic conductors this graph is VI graph is a straight line proportional to this. That means straight line passing through that origin we can write, because this I is proportional to that V you can write, right? So that means mention that the materials which obeys the Ohm's law are called ohmic conductors. The materials which obeys the Ohm's law are called ohmic conductors, or mention another name, linear conductors. The VI graph for such a materials, is a straight line passing through origin, And examples, all conductors you can say, all conductors are ohmic conductors. Next, the materials which does not obey the Ohm's law are non-ohmic conductors, or non-linear conductors. The VI graph for such a materials is non-linear. Which depends on the type of, it is non-linear, and which depends on the shape of the curve depends on the device. For diodes in forward bias, we can express like this. Sorry, this is I and this is V. In forward bias actually, in reverse bias later we will discuss that. So simply draw that graph. We will discuss more about non-ohmic. That means we can say examples as all semiconducting devices you can say, like PN junction diode and transistor, thermistor, all those are non-ohmic conductors. That does not obey the Ohm's law. So you should remember that does not obey the Ohm's law means V is not proportional to I. So even for such a conductors also for the small intervals we can apply this V is equal to IR formula. V is equal to IR is a formula, mathematical relation between potential difference and current, and V is directly proportional to I is the Ohm's law. That you should remember that. So that means here for the non-ohmic conductors we already mentioned that this VI graph is never be a straight line. So it never be a straight line means automatically that indicates that they are not proportional to each other, and so they should not obey that means they are not obeying that Ohm's law there, right? And regarding this graphs here, you should also remember sometimes we need to calculate the resistance from this graph here. So that is about ohmic and non-ohmic conductors. So it is not Ohm's law is not a universal law because it is not obeyed by all the materials or all the devices there. So that means suppose from this VI graph we need to calculate the resistance like this. Suppose it is making an angle theta here, then slope I can write it as slope of the material tan theta is equal to, we can write like V by I or dV by di we can write. So which is nothing but V by I is nothing but our resistance. Therefore I can write this as resistance R is equal to slope we can write. If you are taking current on this x axis and potential difference on the y axis, slope or which is nothing but tan theta if theta value is given. If for example if I am taking this current on this y axis and the potential difference on the x axis, right, if the graph is taken like this, and so now in that case we can write this as so here this slope is equal to, let us say tan theta is equal to I by V, right. Now the resistance is equal to, resistance R is equal to V by I we need to write, so which is nothing but reciprocal of this slope we need to write here. That means in that case if it is given I is on the y axis, then reciprocal of slope will represent the resistance, and in case of this I is taken on this x axis, then the slope directly will represent as resistance of this conductor there, right, resistance there. And actually for the non-ohmic conductors also we define the resistance like that, which we call actually dynamic resistance. We can calculate like this by taking the small elements like this. This is say V and this is IA, suppose I am writing here. Then the slope I can write, the resistance I can write it as resistance R is equal to delta V by delta I we can write, which is the reciprocal of the slope at that point. Now here slope is variable here. That means from this what I mean to say is V is equal to IR relation is valid for that also for a particular region. And so that means V is equal to IR or the resistance we can calculate by using V by R formula. It is not a Ohm's law. V by R is equal to V by I is not a Ohm's law. So Ohm's law means you should remember V is directly proportional to I. That means VI graph should be a straight line. V is equal to IR is just a formula or a mathematical relation we can say, right? So for this non-ohmic conductors also we can use this relation here, that you should remember. V is equal to IR relation or R is equal to V by I can be applied, and generally it will be applied like this. That means here the resistance is variable here. For the different potential differences, you will get the different resistances. But whereas for the ohmic resistance, the ohmic conductors, the resistance of the conductor will be constant in general, right? When the temperature remains constant. So that is about ohmic and non-ohmic conductors. And so next year we define about the resistance and we discuss about more about the resistance here. So resistance so resistance is nothing but opposition to the flow of charges or flow of electrons in case of a conductor or flow of charges in general, right? That rate of flow of charges is nothing but we are saying it as a current. And now here this resistance is nothing but opposition to the flow of charges. So when the charges are moving through that material, there will be some opposition. So you should remember that opposition is nothing but we discussed it when we were discussing the drift well arcs in the previous class. So when the electric field is applied, the electrons are making collisions with those lattice ions, and again they are accelerating, right? So when they are colliding with the lattice ions, they are losing a part of their energy, and so that energy will be actually transferred to that material. That means lattice ions. And so the temperature, the vibration of the amplitude of vibration of those ions will increase. When amplitude of the vibration of those ions increase, that is nothing but we say the temperature of that materials will increase finally there. So that is nothing but the reason why when the current is flowing through a conductor, it gets heated. The temperature of such a materials will increase whenever current is flowing through it, right? I think all of you had observed that whenever current is allowed for some time through a conductor and again switch off that circuit, and if you are just touching that wire, you can feel the hotness, or simply if you are when you are touching the bulb, you can feel the hotness there, and that means there whenever current is flowing through them, some heat energy will be produced in that, and so that heat energy is because of this resistance only. So the resistance is nothing but opposition to the flow of charges. So opposition to the flow of charges is nothing but resistance. So that opposition is nothing but in the form of that collisions will take place, that opposition there, right? So when the electrons they are not traveling freely throughout this material, like a car is traveling on a highway, they are not traveling freely throughout that material. So lot of opposition, that means it is undergoing lot of collisions inside that conductor there. So because of each collision, it is losing a part of energy. And since the electric field is there, again it is accelerating. That means again it is gaining kinetic energy. Again it will collide the another ion and it will lose the energy there, right? And so that's a continuous process when the current is flowing through the conductors. So that is nothing but we consider as opposition, or that is nothing but the opposition to the flow of charges there. So first write the definition, general meaning of this resistance. The opposition to the flow of charges is called a resistance. Mathematically it can be defined as the ratio of potential difference across the conductor to current flowing through it. Right? So this is a mathematical definition of this resistance. And so now from this we can write the unit as potential difference means volt per ampere. And so right, and this actually here we call that as ohm. So ohm is a unit of this resistance, and it is the symbol for this ohm is like this. So ohm, which is the name of that scientist, and so now the symbolic representation of this ohm is like this. We represent with that omega. So that is a resistance unit. So we represent that. Suppose if the resistance is 10 ohms, just we write like this. So that indicates it is the 10 ohms. If it is suppose say 5 ohms, so then we write like this. So that is the 5 ohms resistance there. So that is a symbolic representation of this ohm, right? And next here the circuit symbol. The circuit symbol of resistance is, so we represent in circuits, we represent like this. So this will be the representation of the resistance there. Whenever you are observing such a symbol in a circuit, so that is the resistance, right? And if it is variable resistance, and if the resistance is variable, then it represent like this. We put an arrow above this. So that means if an arrow is like this, a crossed arrow is there like this, generally it indicates it is a variable. Whenever it is this is a variable, for any quantity we can represent like this. We know battery will be represented like this, right? So then if it is an arrow is placed across this, means that indicates the EMF of that cell will be EMF of the cell can be varied, or the potential difference across the cell can be varied. Variable potential difference, we can say that. So later in the battery when you are discussing EMF, we can say that. So whenever such a symbol is there, arrow symbol is there, that indicates it's a variable, and it's a variable resistance there. And so next one more similar to this, one more rheostat will be there. Rheostat is also in order to adjust the resistance only, variable resistance only, and just we can put the desired current in that circuit there. So now the arrow will be placed like this. This is a symbol of that rheostat. So rheostat is also a variable resistance only. That means if you want to allow, for example, a particular current in that circuit, if you want to allow the only 5 ohms in that 5 milliamperes in that circuit, then we can adjust the rheostat until you will get this 5 milliamperes in that circuit. And so this is the variable resistance only. So this is a one way of representing the rheostat, or this is directly the variable resistance, like a resistance boxes will be there, which we can put a desired value in that resistance box. And this is the standard resistance, fixed value. So these are the, all these are the resistances only, right? So that means such a zigzag is there, means that indicates it's a resistance. That's a symbol there. And next here, this resistance will depend on some factors. Can you say on what factors this does this resistance depends? So write that resistance depends on nature of material, comma, dimensions of the material, comma, impurities present in it, and the temperature, of the material. That means on the temperature. That means it depends on those factors there. It depends on the nature of material. Nature of material means if you are taking copper, you will get one resistance, and if you are taking this iron, you will get another, and if you are taking some silver, you will get another resistance there. So it is different for different materials, right? And it also depends on the dimensions. That means same copper wire of different dimensions if you are taking 1 meter length, 2 meter length, and half meter length if you are taking, then resistance, even though all are made up of copper material, their resistances will be different, right? So that means it also depends on the dimensions, how much length is there and how much cross section is there. It depends on the dimensions. Next, it also depends on the impurities. So that means in impurities means, I think its impurity role will be there, major role will be there in case of semiconductors. I think that part may be there in our lower classes. Doping word, doping. Doping is nothing but adding of impurities to the pure semiconductor. If you are taking a pure semiconducting material, and if you are adding some impurities to the pure semiconducting material, then its conductivity will changes by a large amount. So that means the impurities also decides the conductivity of these materials. That means conductivity in the sense we can say resistance of those materials. So that means that is the impurities also can affect the resistance of the material there, right? And next is the temperature. And so the effect of the temperature we will discuss separately. And so then how the temperature will affect the resistance of the conductors and how it affects the semiconductors. So we will discuss that separately. So here these are the major factors which affect the resistance there, right? And so now as I mentioned about the impurities, so just mention a sentence about the impurities, and we will discuss about the dimensions in detail, and about the temperature we will discuss after the dimensions, right? So then first write about the impurities there. In case of, that means conductors, its effect will be different, and in case of semiconductors its effects will be different, the role of that impurities. So just mention a point there. In case of conductors, resistance increases, increases with increase in impurities, But in case of semiconductors, resistance decreases with increase in temperature, with increase in impurities, right? So now let us see about the dimensions, how it depends on the dimensions there. So they mentioned that, as the next point, the resistance of a conductor is directly proportional to its length and is inversely proportional to the area of cross section, So that is R is proportional to L, and Y is mathematical relations. So I can write this as R is proportional to L by A, and so here we introduce a constant here. So rho L by A. I think all of you know about these relations. It is there in school level also, right? So R is equal to rho L by A. So where L is length of the material and rho is the resistivity of the material or specific resistance, and A is the area of cross section. So here this rho is specific resistance or resistivity. So it is the meaning of this rho here, which we introduced already in the relation between E and J. We already introduced this specific resistance or resistivity, right? And so here I will mention the major difference between resistivity and resistance here. So you should remember that resistivity is a property of the material or a property of this that material, whereas the resistance is a property of the body. So your body in the sense, suppose as I said, I am taking this a copper of 1 meter length and a copper of half meter length. Now the resistance of this 1 meter length and half meter length wires will be same. Resistivity is same because both are made up of same material. But the resistance is different because their dimensions are different, or both the bodies are different bodies, right? So resistivity is a property of the body, a property of the material, and it does not depend on the dimensions. So that is the important difference between this resistivity and the resistance here, right? So resistivity does not depend on the dimensions. It only depends on the nature of materials and impurities and temperature, only these factors. So we need to eliminate that temperature dimensions which we mentioned in the resistance there, right? So then that is the importance of this resistivity there. So mention that point also here about the resistivity. Resistivity depends on nature of material, impurities and temperature, but it does not depend on the dimensions. but it does not depends on the dimensions. That is the important point, underline that. It does not depend on the dimensions in the sense. So that is a major difference between resistance and resistivity there. So the resistivity is independent of the dimensions and the resistance will depend on the dimensions, right? And now here from this I can write this units for this. So rho is equal to, I can write this as R into A by L. So now let us write the units for this. So then ohm, this is meter square per meter, and so then this is nothing but we can mention this as the unit of this resistivity as ohm meter. So ohm meter is a unit of this resistivity. So mention that is a unit. The unit of this resistivity is ohm meter. And next, the reciprocal of resistance, resistivity, that is now we called conductivity. Here mention those definitions also. Conductivity. So conductivity is we represent with the sigma. So the reciprocal of resistivity is called conductivity. The reciprocal of resistivity is called conductivity. So then the unit also we can write this as ohm meter inverse, or which is nothing but we can mention this as mho per meter, or I will write like this, mho per meter. That mho per meter is nothing but ohm inverse. That ohm inverse is nothing but we consider as mho, or the symbol also will be reversed there. So that means this can also be written as ohm means we write like omega. That means this is our symbol for this ohm. Then reciprocal of ohm means then we write like this. This ohm inverse means we write this symbol as mho, and its symbol is represented like this, right? So ohm inverse is mentioned as mho, that is we write it as mho, just we need to reverse that order of the letters, and then next omega symbol is also reversed there, that is the symbolic representation of that mho. And so then so that is conductivity unit there, right? Conductivity is nothing but reciprocal of resistance, and then we mention like this. And actually here the reciprocal of resistance is also one word is there, so that we call conductance. So mention that also, conductance. So generally it is represented with this G, that G is nothing but 1 by R. Reciprocal of resistance. So reciprocal of resistance is nothing but our conductance. So mention that conductance. The reciprocal of resistance is called conductance, right? The reciprocal of resistance is called conductance. And so the unit we can write as ohm inverse, or I can write mho, which is represented like this, and it is also mentioned as Simon. Simon is a unit of this conductance. So that means there also we can write here the Simon per meter we can write here, instead of this mho we can write it as Simon per meter, that is a unit of this conductance here. So these are the simple definitions you need to remember there. So resistance reciprocal is conductance, and resistivity or specific resistance, and its reciprocal is nothing but conductivity. So conductivity is the reciprocal of resistivity, right? Now let us come back to this relation here. R is equal to rho L by A. There will be a lot of problems basing on this. So next see this different forms of this R is equal to rho L by A. So we can express this in different forms here. So different forms in the sense, so whenever suppose if you are stretching the material, when the wire is stretched, right? So then I can write this as when a wire is stretched. So when a wire is stretched, then that means It's when the wire is stretched, then we know its length will changes and area of cross section also changes. Suppose if you are taking a conductor of like this, and we are stretching this by applying force like this, and this point we discussed already in this elasticity topics. So when you are stretching this, the area of cross section will decrease and the length will increase here, right? So that means now the length of this wire is increasing, but area of cross section is decreasing here. So initially suppose say L and A if I consider, then this will be L dash and A dash we may consider here, right? So length and area of cross section are changing. So that means here we assume that volume of that material will remain constant. So that means now we stretch the material such that the volume of the material remains constant, but length and area of cross section are changing there. So I can write this expression as when a wire is stretched, then both length and area of cross section changes. Area of cross section changes. Therefore, we are taking like this, right? But volume remains constant. So therefore, this volume of the conductor I can write this as L into A, so which is equal to L dash into A dash. So just we are converting this equation here. So therefore, that equation I can write this as R is equal to rho L square by A into L. Just I am dividing and multiplying with this L. So now this L into A is nothing but our volume. So that volume will remain constant here. So rho L square by V, that volume, A into L is nothing but. So that means I can write this as R is proportional to L square. Should remember this, when wire is stretched, or in general R is proportional to L. When area of cross section remains constant, then R is proportional to L you will get. But whenever area of cross section is stretched, then actually to find the final resistance, R is equal to rho L dash by A dash we need to consider. So instead of that, you can directly consider this relation here. R is directly proportional to L. So that means we can write this as R1 by or R2 by R1 is equal to, from this, R2 by R1 is equal to L2 by L1 whole square we can write here, or L by L dash ratio we can write here, because we are taking this as L and L dash, right? So that ratio we can take directly, and from this we can calculate R2 value if initial length and final length is given. For example, a wire is stretched such that its length is doubled. If such information is given, then L dash is nothing but 2L we need to substitute there. So that means 2L by 2, the 4 times resistance will be increased by 4 times. So such a questions you can directly answer if you remember this equation. So whenever a wire is stretched, you can use this equation. So in the same problem, sometimes instead of giving the information about the length, they may give the information about area of cross section, or they may give information about the radius of cross section. That means a wire is stretched such that the radius of cross section is reduced to half. So then we can write such a similar relation in terms of area of cross section. So I can write this as, so now I am taking this again, R is equal to rho L by A. Now I am multiplying and dividing with A, right? And so now this equation I can write this as rho L into A by A square, or which is nothing but I can write this as rho into V by A square I can write. So again V is a constant, therefore I can write this as inversely proportional to A square, right? Therefore this R2 by, this is now the relation here. So R2 by R1 we can write this as A2 by A1, sorry, inverse relation. So A1 by A2 you will get. So A1 by A2 whole square, right? And that relation in terms of radius if you want to write. So radius is nothing but pi r square you can write. So I can write this as R1 by R2 whole power 4 you can write. Because A is nothing but pi r square. So pi r2 square whole square will be there. So then we can express like this, right? So then such a relations we can write there. That means whenever a wire is stretched, you need to remember this relation. If the information is given about area of cross section, then we can use that relation. R is inversely proportional to, instead of A, we need to take A square. A is the general relation under normal conditions. When it is stretched, we need to consider these relations here. So then similarly, if length information in terms of length is given, then we need to take R is proportional to L square, we need to consider. So now, so we can express this, finally this R value as this equation as in different forms like this. R is equal to rho L by A is our basic formula. So let us see the different forms of this. R is equal to rho L by A. So I can express this as rho L square by V, or I can express this as rho V by A square, right? Sometimes the density and mass of the materials will also be given. So then we can replace this V volume of these materials here. So then volume of the material can be replaced as suppose mass by density. So here if this equation if you want to convert, then rho L square into M by mass by density. So mass will be here and density will be here, and rho into M by A square into D. Just remember this. So those are the different forms of that expression rho L by A. Depending on the given situation, we can use that equation. So just here mass, this volume I am replacing as mass by density, and in this expression also you can replace this as mass by density. And so there remember that so here V is volume and D is density and M is the mass of the material here, mass of wire. Right? And the A means area of cross section and L is the length, that you know already, right? And there will be a lot of problems basing on this. Basing on this R is equal to rho L by A. Sometimes the problems may be there in terms of percentage changes. So now write this one problem. So current is allowed to pass through such a cuboid here. Such a three-dimensional block I am taking here. Right? So then this side I am taking as L, and this is B, and this is H, right? So that means now here we need to find the resistance of ratio of maximum resistance to minimum resistance of this block. So write that as a problem. When current is allowed to pass through the block of dimensions L into B into H, and in the order is also you can mention that L is greater than B greater than H. That's order. Allowed to pass through the block of dimensions L into B into H, or L is greater than B greater than H. Then find the ratio of maximum resistance to minimum resistance. Then find the ratio of maximum resistance to minimum resistance. That means for the same block, the resistance value will be different, right? Can you say how it is different for the same block? For the same block, the resistance will be different. So then they are asking the ratio of maximum resistance to minimum resistance of the same block they are asking. Can you say why that resistance is different? So simply when you are changing the direction of flow of current, that means in the resistance dependence you can also add that point there. So the resistance will also depend on the direction of flow of the current also in the given body. So that means now in this block, if current is flowing along this direction, you will get one resistance. and if current is flowing along this direction you will get another resistance, and if current is flowing along this direction you will get another resistance. So that depends on the direction of the block also, that means direction of flow of the current also, because when the direction of current is changing, the dimensions of the block also changes. That means length and area of cross section also changes, and because of that reason that resistance is changing here actually. And so now here we need to find maximum resistance to minimum resistance. So now can you say when the resistance will become maximum, when current is flowing in which direction? So then our formula is, we know the formula, R is equal to rho L by A. This is our formula. So to get the maximum resistance, this length must be maximum and area of cross section should be minimum. So that is nothing but, when length is maximum according to our dimension, then this is nothing but our maximum dimension here. So current should flow along this direction. So for this direction you will get the maximum resistance, right? And so that maximum resistance I can write this as R maximum is equal to rho into L by area of cross section, means this space area we need to write. So which is nothing but B into H, right? This is a equation 1. Now this is the maximum resistance. Then minimum. So now the minimum we need to verify whether it is flowing like this or whether it is flowing like this. When you will get the minimum resistance. So therefore the minimum resistance, this length should be minimum and area of cross section should be maximum. So that is possible only when you are taking this along this direction here, because this H is the least value. So that means then when the current is flowing along this direction, then length is minimum, then more area of cross section you will get. So then automatically the resistance will be minimum there. Therefore I can write this minimum resistance is equal to, right? And so then R minimum is equal to rho into that length is H by area of cross section is L into B. That's the area of cross section. This space area we need to write. This is L and this is B, right? And therefore ratio of maximum resistance to minimum resistance we need to answer here. So that is rho L by B into H by this is rho into H by L into B. Therefore this R maximum by R minimum is equal to, so I can write this as, so then this rho will be cancelled and you can cancel those terms there. So then I can write this as L square by H square, right? That means this term you can write like this. That means then this L and L we are multiplying, that this rho and rho term will be cancelled, H square, and this B term will be cancelled there, right? So then that is our L square by H square you can write there. So that is a ratio of this maximum resistance to minimum resistance there, right? So next let us see this one more problem basing on this simple rho L by A relation. So that is nothing but suppose I am taking the situation like some mercury is taken in this, a cylindrical vessel. So this is completely filled with this mercury here. This radius is say R and this height is 2R. I am taking this as smaller. So that means some mercury is taken in a cylindrical container, write that problem. So mercury is taken in a cylindrical container of radius R and height 2R. Radius R and height 2R. Then its resistance is R. Then its resistance is R. When the same mercury is poured in another, when the same mercury is poured in another cylindrical container, of radius R by 2, then find its resistance. So here you can solve it simply here, because Here when you are pouring the liquid from one container to another container, why the resistance is changing means the dimensions of that conductor are changing. Now this will behave like a conductor for us when current is flowing through it. And so now when it is poured in this, here initial length is 2r. Now the length of this conductor will changes when you are pouring in a narrow container, right? Suppose this length is increasing up to here. I am taking this length as some L. So since the volume remains constant, so volume V is equal to then pi r square into H we can write, and therefore that I can write this as that H is nothing but 2r. Here I am substituting directly. This is for this case, and here I can write this as pi r by 2 whole square into L. So then from that you can find the L value here. So therefore it is that pi r square you can cancel here, then L is equal to 8 you will get 8r. That means here pi r square will be cancelled, 4 you will get, and 4 into 2 8r you will get, right? Then that is our length now. Therefore I can write this resistance R2 by R1 is equal to L2 by A2 into A1 by L1. Ratio just I am taking rho L2 by A2 by rho L1 by A1 we need to write. That rho term will be cancelled because it is the same liquid. So then this will be the ratio here. So therefore R2 by this is given as R, and this I can write this as A1 by A2 into L2 by L1. Length is direct ratio and the area of cross section is inverse ratio. Therefore I can write this as R2 is equal to R into, then A2 by A1 ratio is you can write like this, pi r square, and this is pi r square by 4, right? And this L2 value is 8r by L1r is 2r, and so that I can write this as R2 is equal to, you can write this expression as like 16r. So resistance is changing by 16 times. So the increasing by 16 times you can write. And actually instead of doing all this calculation, this also can directly solve by our stretched wire method, because here also volume of the liquid is constant, and in stretched wire also volume of the liquid is volume of that wire is constant. So in case of stretched wire, when the area of cross section is when you know the information about area of cross section, then R is inversely proportional to A square, or it is inversely proportional to R power 4 we need to write, right, where R is the radius of cross section. Then here you can observe this radius of cross section is decreasing by 2 times. Then the total resistance will increase by R power 2 power 4 times. That means you can directly take this, basing on this relation, you can directly take this R2 by R1 is equal to, I can write this as R1 by R2 whole power 4 we can write. So which is nothing but R by 2 whole power 4. So which is nothing but 16 you can write. Therefore this R2 is equal to 16R you can write. So if you are using this method, you can solve it easily, since the volume remains constant, or otherwise this will be the general procedure there. So we need to find the length here, and then we need to use R is equal to rho L by equation. So since volume is constant, you can also approach this method here. So like that there will be many problems based on this. And next some more in the next class I will explain some more problems based on this, including that percentage calculations based on this R is equal to rho L by equation. And so then in the resistance of non-uniform cross section or variable conductivity also I will explain the next class, right? You can complete some problems basing on this R is equal to rho L by equation. In level 1 and level 2, level 3 problems you can solve simply basing on this equation here, right? Thank you.